Pluto from forgotten dwarf planet to ocean world candidate in 2006. The International Astronomical Union redefined what it means to be a planet. Under the new classification, Pluto was recategorized as a dwarf planet, a decision that caused widespread debate and disappointment. Once celebrated as the ninth planet of the solar system, Pluto was suddenly regarded as a minor icy body in the distant Kuiper Belt. For many, it became a forgotten relic, frozen, lifeless, and scientifically unimportant. Yet today, that perception is undergoing a dramatic transformation. With new evidence from spacecraft missions and powerful telescopes, such as the James Webb Space Telescope, JWST, Pluto is being reintroduced to the scientific stage, not as a static frozen rock, but as a complex, active, and potentially habitable world. The iconic heart of Pluto. One of Pluto's most recognizable features is Sputnik Planitia, the vast heart-shaped glacier dominating one hemisphere. This region is primarily composed of frozen nitrogen, with traces of carbon monoxide and methane. Its significance extends far beyond appearance. The mass of this ice sheet is so great that it alters Pluto's rotational stability, effectively acting as a counterweight. What lies beneath, however, may be even more important. Many planetary scientists believe that beneath Sputnik Planitia exists a subsurface ocean of liquid water preserved by heat generated within Pluto's rocky core. This heat arises from the slow radioactive decay of elements, a process still active after billions of years. Despite Pluto's great distance from the Sun, such internal heating could maintain liquid reservoirs, preventing complete freezing of its interior. The existence of subsurface oceans elsewhere in the solar system, such as beneath the ice of Europa and Enceladus, provides strong precedent. If Pluto too harbors liquid water, it would represent yet another potential habitat in a region once dismissed as sterile. Geological evidence of activity support for this ocean hypothesis comes from Pluto's surface geology. Images captured during NASA's New Horizons flyby in 2015 revealed fault lines, fractures, ridges, and evidence of glacial flow. These features strongly suggest that Pluto's surface is geologically young and active, not ancient and static as once assumed. Some areas display evidence of convection, where heat from below drives the slow overturn of ice layers of the surface. Other regions suggest tectonic stretching, which could be caused by internal expansion as subsurface water gradually freezes and increases in volume. These are not traits of a geologically dead world. Pluto and Charon. A binary system equally fascinating is Pluto's gravitational relationship with its largest moon, Charon. Rather than Charon simply orbiting Pluto, the two bodies orbit a shared point in space between them, a rare situation known as a binary system. This interaction generates significant tidal forces which may help maintain internal heat within Pluto and possibly within Charon as well. Charon itself shows evidence of past tectonic activity, including enormous chasms and ridges. Its poles display unusual red deposits thought to form when gases from Pluto's atmosphere escape and freeze on a Charon surface. This exchange of material highlights the complexity of the Pluto-Charon system, where both bodies may influence each other's evolution in ways not yet fully understood. The possibility of life. The discovery of a subsurface ocean naturally leads to one of the most important questions in planetary science. Could Pluto support life? If liquid water is present, microbial organisms might exist beneath the thick, icy shell, shielded from cosmic radiation and extreme surface cold. These organisms, if real, would live in conditions radically different from Earth. Total darkness, immense pressure, and extremely low temperatures. Yet on Earth, life has been found in hydrothermal vents, subglacial lakes, and other extreme environments. The existence of microbes on Pluto cannot be ruled out. Adding to the intrigue, JWST and earlier data from New Horizons have revealed unusual chemical patterns in Pluto's atmosphere and surface. Complex organic molecules, including tholins, form when ultraviolet sunlight interacts with atmospheric gases. The lines are not living matter, but are considered prebiotic molecules that may contribute to life's chemistry. Some heat signatures and chemical anomalies detected beneath Pluto's crust remain unexplained. These signals could eventually turn out to be the fingerprints of ordinary geological processes, perhaps cryovolcanism or chemical reactions between rock and water deep below the surface. But to some researchers, they hint at something far more profound: the possibility of chemistry resembling that associated with life on Earth. If even the faintest biological processes are shaping Pluto's subsurface layers, it would force us to rewrite the boundaries of habitability. Life, we often assume, needs sunlight, warmth, and a temperate climate. Pluto has none of these, and yet its hidden world may still be alive in ways we do not yet understand. Pluto's thin but active atmosphere for such a small and distant body. Pluto possesses a surprisingly dynamic atmosphere, composed mainly of nitrogen with traces of methane and carbon monoxide. It is delicate and ever-changing. Unlike Earth, Pluto's atmosphere is not permanent. It is in a constant cycle of collapse and rebirth. During colder seasons, gases freeze onto the surface, coating the landscape with frost. As temperatures shift, those same ices sublimate back into vapor, replenishing the thin atmosphere. This constant exchange makes Pluto's sky an active breathing system despite its fragility. One of its most striking features is the reddish haze that envelopes the planet. This haze is formed by complex organic molecules known as tholins created when ultraviolet light interacts with methane and other gases. As tholins drift downward, they settle on Pluto's surface, painting it in subtle shades of red, brown, and orange. But the lines are more than just colorants on Earth. And in laboratory experiments, they are seen as prebiotic molecules, chemical precursors that could eventually give rise to life. Their presence on Pluto suggests that even in the farthest, coldest reaches of the solar system, chemistry essential to life can naturally arise and persist for billions of years. Beyond Pluto, the Kuiper Belt connection, Pluto's significance extends beyond itself. It is the largest and most well-studied body in the Kuiper Belt, a vast region of icy worlds beyond Neptune that are remnants from the solar system's earliest days. Most Kuiper Belt objects appear inert, frozen, and geologically dead. But Pluto is different. It has flowing glaciers, surface fractures, a dynamic atmosphere, and possibly a liquid ocean hidden beneath ice. Its activity makes it an outlier, a world that refuses to conform to expectations. If Pluto can sustain internal heat, chemical reactions, and possibly even habitability, then other Kuiper Belt objects may do the same. Worlds like Eris, Make, and Haumea could also hold hidden oceans or complex organic chemistry. In this way, Pluto becomes a gateway to understanding an entire population of distant worlds. Studying Pluto is not just about solving its mysteries. It is about learning whether the Kuiper Belt as a whole might be a cradle of exotic environments, worlds shaped by ice and time waiting to be explored. Unanswered questions. Despite the breakthroughs of the past decade, Pluto remains a world of riddles. Many critical questions are still unanswered. Does Pluto have a magnetic field? Some indirect hints suggest it might, generated by interactions within its core and ocean. If confirmed, such a field could shield its atmosphere and subsurface water from solar wind, providing stability over billions of years. How stable is the ocean? Could it survive for billions of years without freezing? Or does it exist in cycles of melting and refreezing? Is there active cryovolcanism? Some surface features appear to be icy volcanoes, suggesting internal material may still be escaping to the surface. Most importantly, does life exist? If microbial organisms exist beneath Pluto's crust, they would represent not just survival in extreme conditions, but a second genesis of life within our own solar system. To answer these questions, we will need new missions. The 2015 New Horizons flyby provided extraordinary data, but it was only a brief encounter. Future orbiters could watch Pluto over months or years, mapping its changing atmosphere and surface. Landers could study its chemistry up close. One day, advanced probes may drill into the ice, searching directly for liquid water and possible biology. Such missions would be difficult. Pluto lies nearly 6 billion kilometers away. A journey there takes close to a decade, and technology must be developed to survive its hostile conditions. Yet the potential rewards are immense, offering insight into the origins of oceans, atmospheres, and life itself.